I'm Roy Clark, Professor of Physics and co-host, along with my colleague, Professor Tim Chupp, of this program of public lectures. It's my great pleasure and honor to introduce our speaker today, Dr. Anna Stefanopoulou, the William Clay Ford Professor of Technology and Professor of Mechanical Engineering at the University of Michigan. Dr. Stefanopoulou leads a regarded interdisciplinary group researching electrical and thermomechanical processes for battery management, fuel cells, and engines. And this, of course, is a very important area for not only for electric vehicle propulsion, but for renewable energy applications also. Dr. Stefanopoulou was an assistant professor at the University of California, Santa Barbara, before coming to Michigan. She has been a visiting professor at ETH Zurich in Switzerland and a technical specialist at the Ford Motor Company. She earned her undergraduate degree in naval architecture and marine engineering at the National Technical University in Athens, Greece, and her PhD was earned in the Electrical Engineering and Computer Science Department here at the University of Michigan in Ann Arbor. Dr. Stefanopoulou is a fellow of no less than 3 professional societies, including the IEEE and the Professional Society for Mechanical Engineering. And she has received numerous awards from those professional organizations. Following our presentation, Dr. Stefanopoulou will be pleased to answer any questions that you have. And we ask that you email those to us at physics.umich.edu. And also, if you're in the audience here, please, you can also write your question on a card. And if you wish to do that, sort of wave it around a bit so that we can see and come and collect it from you at the end of the lecture. Now, without further ado, let's have a big hand for Anna, and please take it away.
Okay, turned on microphone. You can hear me. Good morning again. Super. So yeah, I am totally honored. As Roy said, I am honored to be in the Saturday morning physics. Actually, when I say it, it almost feels like it should be Saturday Night Live, right? Kind of thing. It won't be that entertaining, but it will be informative. Okay, so I am honored. I am from just few blocks, actually. You can almost walk. Let's see if this works. At the Auto Lab. So I work actually at the Automotive Laboratory at North Campus. It's where the College of Engineering is, and we call it, it's this ground zero of automotive engineering, mobility engineering, and propulsion and powertrain development. And it has been there, and we've been doing this for 40, 50 actually years now. So what you see is that we obviously have developed a lot of technologies, leadership, but also that went to all these companies, and this map keeps on changing. But we also have the responsibility for understanding and improving and controlling, reducing emissions. So this graph here keeps on evolving and changing. We all are aware of climate crisis and how much transportation is actually contributing to this climate warming. Transportation globally, it's nearly 20%. In the US, it's 29%. In California, for example, it's closer to 40% of the greenhouse gases. So it's a local and a global problem. Out of this transportation sector, 15% are passenger vehicles, you and I, and 5% are the commercial sector. Definitely a lot of leadership and a lot of heritage and a lot of responsibility out of this. So I have to say, like Roy said, I worked in the beginning, my PhD was actually controlling engines. And I worked and grew in the engine world, developing fuel economy, efficient, highly efficient engines, and emission control. This is a graph a colleague of mine, George Lavoie, developed. As you can see, it shows over 100 years, actually, sorry, more than that. This is the path of internal combustion engines and how they have improved their fuel efficiency, miles per gallon, has improved over the years. You can see the birth, and you can see several projections and legislative actions that we did or did not follow. So let's see a little bit. Of course, the big takeaway message out of this graph is the work we did for the last 25 years, since 1975, when the EPA was established and they set up emission control systems for vehicles. We have actually saved 2 trillion gallons of fuel. This is a lot of improvements that we have seen throughout this last 30, 40 years. And you see here our current gasoline, diesel, and hybrid fuel efficiency standards that have been set and we're trying to meet. But it is now a new kid in the block, which is the lithium-ion batteries. So since this is a physics lab, physics seminar, I just had to use, close to chemistry, I had to use the periodic table. My daughter says, oh, I remember that. So lithium is just light, it's just a little bit heavier, just below hydrogen and helium. And because it's light, and it also has very high potential to actually shed its electron. It's on that one layer here outside space that can be actually shared. That means that it's actually very, let's say, volatile, but in fact it's energetic, it has a lot of power, and therefore power density because it's also light. I've been always been asked about where are we? Where are we with respect to switching to electric vehicles, and is it true that we will improve? And there are a lot of numbers that are out there, and I want to make sure that you have, you get out, you take with you this graph. It has been developed in a paper, as you can see recently, 2022. It reflects the existing grid conditions, and it shows the greenhouse gas emissions at different counties in the United States. Counties and where it is matters. And that's why there are a lot of numbers that have been out there, and people are debating, and debate is excellent, as long as we understand also some of the facts that where the obviously electric vehicles, so what I'm showing you here is a internal combustion engine column, hybrid electric vehicle column, and battery electric vehicle column. And the rows correspond to if you were to drive a sedan, an SUV, or a pickup truck. So ideally, we want to go from this totally red, that it's a lot of carbon dioxide emitted per mile, to the battery electric vehicle, as smallest as possible vehicle, and electric. So that is, we want to go from the bottom left to the top right, as much as possible, as fast as possible. You can see that this picture, there are obviously counties that they are not as, they can improve, and there are some areas that because of the renewables and their sourcing, the battery electric vehicle is way better, very, very small footprint in carbon greenhouse gas emissions. So I would like you to consider this in your discussions and in your further consideration about what you would buy next. And with that, that's my kind of like preaching here. So we are entering indeed in a battery bonanza era where batteries and electric vehicles are the fastest way to decarbonization of the transportation sector. And it would be, in fact, a key element no matter what other player will come in light and in practice. What you see to the right is actually what we need to have in place in order to avoid or at least maintain the 1.75 degrees Celsius climate warming. This kind of arrow that shows there in the yellow space, if you actually read it, it's 500 million vehicles that we need to have globally by 2035 if we want to stay in the 1.75. So please, what do I want to say? Please go buy electric vehicle. No, you should keep you should buy the most efficient vehicle that you can buy and you can afford at this point. And you can see here that in the US goal, we have 50% of light duty vehicle sales by 2035. That's 10 million vehicles. 10 million vehicles to actually create EV per year to be sold. It is a very steep, very tall goal. And I want to be also pragmatic. To do that, we need to produce something like 2,000 prismatic cells per minute in the United States if we want to actually produce and consume, use these cells. So it is a very difficult task we have in front of us. So I will continue by saying these cells, obviously, that we will be producing, we know we use our vehicles for more than a decade. In fact, in some countries, they use these vehicles for nearly 2 decades. Vehicles get sold and bought 3 to 4 times in auctions all around the world, right? So these vehicles are going to stay, and they're going to have batteries in them. So we don't want to turn this battery bonanza to what I call, perhaps battery disaster. And in a sense, we want to be able to monitor, manage, and be very careful and safe in our way of deploying and using these batteries. And the truth is, batteries are like humans. So I like to say that we hate to be overworked. They do too. They hate over temperature, over pressure, and we're diverse in size, in chemistry, and shape. Okay, that's the only place I actually would prefer if we had a little bit less diversity and a little bit more standardization. But batteries are produced, and they are statistically faulty, and they're all going to die. So very much, like humans. So we need a battery management system, and the functionality of a battery management system that manages these sensitivities. Their powerful devices come with sensitivities and critical behavior and performance that needs to be managed. So what you see here is we start in the battery management system, high-level functionality. We need to measure current, voltage, temperature, and based on that, we estimate the state of charge, how much energy is left. It's your fuel gauge. Then what we do is we also estimate state of health, and I will get a lot into that, and aging, because as I alluded in my previous slide, we want to make sure we manage actually these assets for a long time. And of course, safety. We have a lot of cells in a pack, 300, sometimes to 7,000 cells. So we need to be able to balance these cells. And at the end, we need to provide power limits and limit to drive them to their safe limit. Okay, so that's what the battery management does, and I'm going to get into it after I introduce you and also our audience. I hope there are students there that will be looking at that, and therefore I used our batteries that we are producing in the battery lab just across my automotive laboratory at the U of M battery lab. We have a fabrication facility, and to the other side, what you see is basically the 5 layers of a basic battery. My daughter drew that, so I had to use it. So 5 layers. You have on the end the electron collectors. So you have aluminum and copper, and then you walk inside, you get inside, and you have the metals and the active material, and then you get in the middle, and you have a separator. Okay, so 5 layers, if you want to remember. So let's take a look and see what happens in these 5 layers. Again, you see the copper, so we have the battery. The battery has a 5-layer, basically all this 5-layer is rolled up like a toilet paper, high-quality toilet paper with 5 layers. So we have this, roll up, and then we stack it inside a can or a pouch or a cylinder, and we make our battery, right? So basically, we have these layers, and these layers have, as I said, the anode, which is typically graphite, carbon. And the carbon, we embed in the carbon is where the lithium gets intercalated and stored. And then we have the cathode, which is typically a metal oxide, expensive stuff with a lot of treatment. And so the lithium, as you see, what happens is in the cathode, that's where we actually ship, and we embed the lithium in the cathode when we first make the batteries. So you can see when the lithium is in here inside and gets stored in the metal oxide, and it can leave the ions and the electron. Because of the separator in between these two, anode and cathode, because there is a separator that does not let electrons through. So only the lithium will go through. The electrons will go around the circuit. So these electrons here get to move on the anode side, get intercalated inside the graphite, and then we have a charged battery. And the ability to go back and forth is what allows us to charge and discharge, and we can actually put them on the vehicles and other applications. Of course, microelectronics was one of the first applications. One of the first was going to NASA, right, and to the moon, and the backpacks that astronauts and other other type of missions we have, even space, are using lithium-ion batteries, but even more complex ones. But let's stick to them. So what I'm going to do now is think about the anode and the cathode. They're like two containers, think about 2 glasses full of lithium. And you're just taking lithium from one glass to the other glass, and they're typically, the way I'm showing you so far is vertical. I'm going to flip them and kind of lay them down, and now I'm going to show you anode and cathode. And this is our cathode, and this is our anode. And what you see in these graphs is as we put lithium inside the graphite, then it becomes more like lithium, right? You put more lithium in the graphite, the graphite becomes more like lithium. So its potential with respect to lithium becomes like lithium, so it becomes 0. So the difference between lithium and carbon that is full of lithium is very small. At the same time, this lithium came from the cathode. So when the lithium leaves the cathode, so this Y here, when we actually are taking lithium out of the cathode, the cathode becomes less and less similar to lithium, and its voltage goes up. And what we measure when we are charging, we are measuring terminal voltage. So we're actually measuring the difference between the cathode and the anode, and we see the terminal voltage which goes up because actually cathode goes up as we are discharging the cathode and charging the anode. Okay, so with that, I want to show you this because it's kind of like, the heart of the of a battery, it's like actually has two hearts. Think about our two parts of our heart. It's the anode and the cathode, and the health and how we manage this depends a lot on keeping both of these safe. And indeed, if we actually, for some reason, drive our X, like we put a lot of lithium in our graphite, then it will start piling up, and then it will create, and that happens when we overcharge, it will create plating and dendrites. So we will create lithium plating instead of intercalating, and the picture looks like that. It's kind of scary, actually reminds me of the coronavirus. We did this graph when the COVID hit. So what you see in this yellow, pokey, these are the dendrites. This is when we are actually charging either very fast, and so the lithium cannot go inside the graphite and intercalate, but piles up and creates these whiskers. And when these whiskers grow, they actually will create a short, right? And so there are other things. When we overcharge, we can actually also dissolve the binders and the copper and the aluminum, and there are things that are happening like the cathode side cracking and opening. So there are actually a lot of interesting chemistry, mechanical, electrochemical, electromechanical, and chemomechanical aspects of it. So what you see, however, is how we are using the cells, and at the end, how they're fading, their capacity fade, and their resistance increases. And unfortunately, we don't have any sensor to tell us what is happening inside. It's like really driving blind. So we really need to be able to connect really the physics of what's happening inside the battery. And these are, I know it's a heavy loaded equations, but hey, I'm not going to go through them. I want to show you, for example, that we actually can have the so-called digital twins, where there are physical or mathematical models of the physics that are happening inside the batteries, and allow us to actually capture the degradation, the performance, and the degradation of the batteries. So what you see here are the equations that correspond to how we charge, discharge, and they're partial, what we call partial differential equations that keep track of the gradients of this lithium concentration, because we don't want it to pile. So we want to keep track of these gradients in our math, in our microcontroller that is in our car. In any microcontroller in the battery management system, that will be almost in every battery that you have, including your cell phone, your computer, and the scooter and everything. So we keep track with these equations. Current comes in, and then we basically have a mathematical copy of the behavior of the physics that are happening, the underlying physics, inside the anode and the cathode. At the same time as we charge-discharge, we keep track of how much capacity we're losing and how much our resistance is increasing. And we actually, this way, keep track of phenomena. So you say, why is this happening? Why am I losing capacity in my cell phone and the time running? So let's look at the mechanisms. So what's happening is you have in every kind of particle that accepts this lithium. So typically lithium goes through and gets soaked and inside slip, intercalated inside the carbon. But you have this film, kind of like a rust, that builds up around every little particle. And therefore, because of this rust that we keep track here, the film of this film increases, the resistance will increase, and this rust captures lithium, and so it actually takes it from going back and forth. It's not reversible anymore. It's stuck on that film. And that's why we're losing capacity, and our resistance increases, and sometimes, our cell phones, when we use it and we talk too much, it kind of gets hot, right? Because there is resistance. And more it ages, it actually gets a little bit hotter. I don't know, have you experienced that? Okay, so we keep track of all that, and not only we monitor it and act on it, we actually anticipate it. So in laboratories, of course, I'm kind of scaring, and I don't want to scare you. All these things are the bad things that are happening that we need to protect. But in fact, our vehicles are indeed tested and warranted, and our devices to run for, let's say, 8 years, 100,000 miles. So our manufacturers will test a lot these devices and make sure they actually fulfill the warranty. And of course, honor it when something bad happens. But in the laboratory, what we want to do is really do what we call accelerated testing and accelerated degradation, where we actually make our cells die really fast. So let's take a look at these aging experiments. What you see here to your, you see two graphs, right? So in these graphs, you will basically, the axis is, the x-axis is amps throughput. Amp hours is basically how much charge did you put in and out, we accumulate it, we keep track of it. And you see now in both the graphs, the one that you see to your, let's see, where am I? The one you see to your left is capacity fade. So you see that this cell started with 5 amp hours capacity, and then it starts dropping. After a while, after many cycles, after some usage, these cells, the red cells, are dying faster. They're losing capacity faster, right? And then the blue less faster, and the green are the slowest. So what are these colors? The red correspond to temperature. That's 45 degrees Celsius cycling. So we do accelerated tests, so we do it in high temperature. Frankly, this is not too high, just to translate the Celsius, right? So we're talking about nearly 100 degrees Fahrenheit. So it's not that high, it's temperature in the summer. The blue lines correspond to -5 Celsius. It's just actually very close to what it's outside there. It's like almost 0. -5 Celsius. And the green correspond to room temperature. So obviously batteries, again, like humans, they don't like high temperature or low temperature. They like room temperature like us, okay? And what you see here is the capacity loss, and what is the important part of capacity loss? Range. It's how far your vehicle will go, how long your cell phone will be used, et cetera, right? And so that is very important. To the right-hand side, you see resistance. So now the same cells, at the same time as they were losing capacity, the resistance, all of them, the resistance will go up. Again, the resistance of the cell that was cycled under high temperature goes faster up. And resistance matters because that's power. Of course, if you had if you have too much resistance, then a lot of your energy from the lithium going back and forth will go to heat, and it will warm it up, and it's losses instead of actually creating power. So that's really, we keep track of that. We have phenomena, as you can see perhaps here. You can see some cells, although they are dying or aging in a linear way that we can extrapolate. We look at how it's doing, and we can actually predict the future. But some of them kind of have what we call the knee. So they start accelerating degradation. They start actually aging faster. So we call this the knees. And you can see that some actually cells have accelerated increase in resistance. And we call this the elbows. so we had a paper, a friend of mine from Edinburgh University in the statistics department, he actually wrote a very nice paper saying correlation between knees and elbows to understand how these things are related and how actually we can predict them in the future. And again, we can do data-driven approaches and just develop empirical maps that tell us about this aging, or as we do in my lab and in many other labs across the world and battery manufacturers, we actually use these digital twin models, these digital twins, to actually predict how lithium concentration, how this rust film will build up around all the particles and build up. And then because it builds up, it will actually create high gradients, and you'll start piling this lithium plating. And when you have this phenomena, then the plating clogs the pores. It makes even more gradients, and it's like a kind of a snowballing effect, we call this. That's what creates the knee and the accelerated degradation. So we're actually keeping track of and trying to predict when that will happen. Okay, so therefore, we have a lot of degradation patterns that we are keeping track at the battery management system with a digital twin. And the pattern matters, how they're dying, how they're aging. So these are 3 graphs. These are 3 different cells. They all have lost capacity. They went from 5 to 3, right? So they have lost quite a bit of their capacity. And they all have lost the same capacity at 1,000 cycles. Do you see it? Right? I'm right, right? Right, 1,000 cycles. All of them. Which one are you going to buy? Or which car would you buy? How does it go? Which car with which cell would you buy? Definitely not the one with the knee, right? Because that had hit the knee, it has hit the accelerated degradation. So that's the point that I'm trying to make here, is that the pattern matters, right? Because you want to know if you have started reaching the knee, because then that is a very important point to, let's say, not buy a second-hand vehicle, or to not use it further and plan for maintenance, or to recycle or repurpose it to another place where it can be used more effectively. So indeed, degradation matter. And that's why the battery management system keeps track of what is happening, and the degradation is happening over its whole life, including looking basically during its use, when we call it the field data, and trying to do this estimation of the resistance increase and capacity fade with some confidence levels. Of course, the farther we are predicting, unfortunately, we're not, we're not the oracle, so we are actually, well, even the oracle was had very low confidence levels. Anyway, so you see here that we are doing this work, and it's very important for module pack replacement, for resale value, and for pack repurposing. And the important part, the most important dire one right now, is the total cost of ownership. So it affects, how people perceive electric vehicles and how they will buy them, because total cost of ownership should include the resale value of it. But it also includes environmental and social aspects about how we're going to actually, when is the end of life, and it's appropriately to actually either repurpose to a different place, to a different application, and or recycle. I'll get to that in a minute. So I'm going to hit you with a few more equations, just because whatever I told you so far it seems to be very physics, right? It's like chemistry and physics, and it's understanding the mechanisms. But actually what I do is math. I do the battery management system. I write the algorithms that keep track of these things and make sure that they actually, in real time, compute these power limits. So allow me to show you a little bit more equations, to tell you a little bit of what the software looks like, or what is the math. And for the students that are doing calculus, and they're taking calculus or pre-calculus, and us that we suffered through perhaps some of these times, I motivate you. This is like really good stuff. And okay, again, I have to say, I'm motivated from a lot of the students that they keep on asking me, oh, that's a lot of math. Do we have to learn all that? So basically, how do we compute power limits? And by that, the actual realization, I'll show it to you, it's to the right. But let me show you, so these equations that I had in this one page, we actually rather simplify them. We simplify them and we make them to equations that we can put current in and predict the voltage out. And therefore, we have an equation, right, that given the current state, that we take it from measurements, we can take current in, predict the voltage out. And guess what? For those students who do calculus and they come up with the inversion, function inversions, we basically take these two equations and invert them and find for a given voltage what should be the current. And in fact, what we're looking for is if there is a voltage limit that is harmful, what should be the minimum or the maximum current, actually the maximum current that we should be sourcing. So that's exactly what we do, and it gets realized in currents, state of charge, and voltage limits we have. And then we write these equations that define the minimum and maximum of these limits, and then predict forward, because we have an equation to predict also forward and future. And guess what? We are the policemen. We are doing power denials. I know it's terrible. It's like I tell my students, like everything is so interesting, and I want to tell you all these things about battery management, but at the end, we are basically denying power that could be limiting and unsafe. That is the ultimate goal and purpose and mission we have in our battery management system. So it just sounds bad, like I'm a power denial, algorithm. So yes, but we have to compute these power limits. And as you see here, what we do is this is somebody that this is actually driving a scooter across town, or a robot that goes back and forth. Actually, it's several days. And it's current, it gets used, and the person can just, open the handles and accelerate. And then at this period here, we calculate that, we are starting to hit the voltage limits down here. You see over here, it hits the minimum voltage limit. We don't want that, because then copper will dissolve on one side of the electrode, like I was telling you. And so we actually we start decreasing the power. Where's the power? Here. We start decreasing the power. At this point here, what happened is, what limit got hit? Can you see? The temperature limit. This thing was used too much, and it was at high temperature conditions. Scooters and things like that don't have good cooling, right? They are very compact. And so it hit a temperature limit, and hey, my controller will tell it not to go to higher temperature, because higher temperature could cause thermal runaway and other things that hopefully I'll show you. And basically what happens at the end here, so it trickle kind of moves. It goes with much lower power. It gets used for a while, and then here it depletes all its charge and stops. It cools down. Night actually comes and starts cooling down, and we're seeing a nice kind of leaned scooter by our lawn in our neighborhood, as you see many of these pins left by students. So this is what we do, power denials, and that's very important. Okay, so obviously this algorithm I showed you, because lithium-ion batteries are actually I said they're diverse in chemistry. We can actually populate our algorithms with the right chemistry, and they can actually scale to every limit and can power and protect not only scooters and vehicles, but obviously much larger installations that we need as we move to renewable energy, and we will have storage. So I want to show you a few more things now that look a little bit also like physics, that they're in the forefront of what we are trying to make sure it's extra safe. And as we're learning about battery behavior and aging, one of the things that is happening, again, batteries are like humans. They grow a little bit. Maybe their waistline grows as they get older. It happens to me Maybe it has happened to you too, right? So what I say is, there are two-dimensional changes in batteries that are happening as they age, and that is not very well known. First of all, the cells breathe. So when they take lithium inside graphite, it's like taking oxygen in your lungs. So they expand, and when they discharge, they contract. Truly, really. Slightly, but they do. The diatomic structure of the graphite, the carbon, is opening when the lithium tucks in. And so they actually open up. And they actually swell like they breathe when they charge and discharge. At the same time, they irreversibly swell. It's like what I said, the aging, kind of like, I always go and buy new size pants, and my new size is actually always, bigger. So like humans, batteries actually get swollen. And why do they? And let me show you the swollen. Remember this rust and this film and all this material, at the end, they actually build up, and so they make the battery slowly kind of grow a little bit, and this is displacement. We tuck our battery, we put our battery inside fixtures like this. We, of course, measure, we take current and take the leads out and take current and measure voltage. But at the same time, we put this kind of probes which measure how, as the battery breathes or swells over time, we can actually measure this displacement. And what we do is we age in our labs our batteries. So this is a battery that has been aged for 10 to the 5th seconds. That means like 4 months. Cycling back to back, back to back, back to back. Really hard, frankly, at high temperature in this particular case. And what you see is the voltage goes up and down. We have seen this before. And this is the fresh voltage, and then the aged voltage is less capacity, right? And then what you see also, the displacement, this is the breathing, charge, discharge, charge, discharge, charge, discharge. But you can see also an irreversible swelling and an expansion happening. And the fresh charge, discharge, and the displacement was this and went back and forth. And after it had lost 30% of its capacity, the aged cell, of course, it cannot swell so much anymore, right? It's like a runner. Like as you age and you don't have enough lung capacity because you lost capacity, you can't have this large breathing capacity. And so that's why the battery actually get expanded and contracted less, but at the same time, it actually grew. And it's interesting, and we're looking at that because it can tell us a lot of things, and it can also tell us about how to package and how to protect the cells. So this is a cell that has aged under 45 degrees Celsius in conditions that correspond to 5 years. They started fresh, and they went to 76% aged capacity, aged based on capacity. This is at -5 degrees, again, the same age, aged conditions. And this is at room temperature, almost the same aged condition. So when it comes to electrical signals, you have the same aging, let's say. Of course, this one took only 5 years, this one 7 years, and this 10 years. Remember, room temperature is good. Okay. But when it comes to electrical signals, you can see that they're very similar. But look at the mechanical, this expansion. The cells that they actually aged under this cold conditions are swollen by 400 microns. That's something like about 7% of the cell width. So it's substantial to actually take into account in our packaging, in our design, and in our overall lifetime projections of the systems, given that the cells are inside a pack, and the pack size doesn't change over life, right? Like I go and buy bigger pants, but the cells are stuck on the same pack size. So when we are basically enclosing them, they start expanding, they feel a lot of stress, they are uncomfortable, and perhaps that accelerates their degradation. So this is the research we do in the forefront of trying to understand conditions and of course, chemistry and materials that would reduce this expansion. But at the same time, we're looking at the overall design. This pressure, of course, matters. You can see that if we apply too little pressure, the cells are aging the least. And if we apply more pressure, they age with this throughput. They age less fast and less fast. But then when we increase the pressure, then it actually starts hurting again. So it's like a Goldilocks principle of there's an optimum pressure that we need to apply throughout the lifetime as they expand. This is what, of course, it's also important how we package cells inside the pack. It is also important for their end of first life. Again, if we want, these cells have very expensive material that they have been mined and have been processed. And so it's very important to be able to use them, potentially repair them, and refurbish them, and keep on using them. Right? So let me ask you a question, right? How many of you are driving your car beyond your warranty? Yeah, that's right. So, and it happens. I'm originally from Greece. I'm from Greece. I grew up, I was educated in Greece, and I went back there last year. And I found out, I did a little bit of research, and I found out the average passenger vehicle in Greece, life of an average passenger vehicle is 16 years. And our average bus, 19 years. We just keep on fixing it. We don't have money to buy a new one. Right? So these vehicles are fixed. We're fixing them, and a lot of countries have a lot of machine shops and remanufacturing industry that keeps them running and going. And I think it is important to design packs that they are repairable and can be remanufactured. And that's why we're looking at this packaging and this pressure to make sure that as they age, they can also be separated easily and can be used and repaired. If there are 1 or 2 faulty cells, then we can repair the module and keep the high value of the pack intact. We're also looking and trying to understand how to repurpose them to the grid, let's say, because if they are not good for the automotive sector, there still can be 75% capacity, can be perhaps used for a little while longer into the grid. The vehicles that are fresh, new today could actually help offset some of the minerals, the mining, and all the energy that we're using to manufacture cells so that they can be used in the grid to support decarbonization and also the economics of fast charging. We need sometimes, because our grid is not so strong, to put storage next to chargers so that we can support them and also help with our bills to take the peak power down from even our homes. So a lot of different second life applications. At the end, as I said, batteries, like everything will fail and die, and we need to be able to have an ability to recycle them. The Department of Energy and many other organizations, national labs and us, we're working very heavily and with a concentration and effort on developing tools and techniques in various recycling methodologies so that we can actually reduce as much as possible the mining that is needed for these batteries. You can see here that energy consumption, water consumption, greenhouse gas emissions, and other emissions are, of course, reduced as you go from mining, which is the, let's say, current state of the art, or typical practice, I should say. And as we're introducing some of this recycling, of course, we're improving a lot of these environmental aspects, but the cost is higher. This one is the best, which we call direct recycling. And to be able to do direct recycling, we have to know the health of the cell quite a bit, and we have to be able to to break it efficiently to smaller pieces. So that's why it's also important, the part that I showed you earlier. So the last 5 minutes I'll take into safety. We all know actually that, well, maybe, we have heard news about recalls and safety incidents. Cells indeed are picky, and they are, as you can see here, they can also we have to be careful in not only managing them when they're active, but also be able to handle them, store them, transport them when they're actually not, the BMS system, let's say, is not active and it's not operational. And therefore we have, this is this is a cell phone, okay? I'm referring to my daughter a lot. She obviously gave me a lot of tips last night about making this presentation a little bit more accessible to her and her peers. So what you see there is actually a cell phone that has actually popped, cracked open. Some of you probably have had iPads or computers that have been a little bit, your trackpad doesn't work very much. Well, that's because batteries do have gas evolution like this, that if you, in high temperature, they can actually swell like that, and we need to be able to detect this phenomena. Make sure you check in your shoe boxes where you store all your old cells and iPads inside your closet. Sometimes you might end up seeing something like this. So what happens is we need to actually, like I said, understand when abnormal swelling happens. That is the perfect indicator that things start happening in a wrong way, and therefore we need to put in place mechanisms to actually minimize the risk and manage the risk and handle these cells. So we have basically cell swelling, and then there is a safety. So let me, with this swelling, we will detect abnormality. And then typically when you can't stop this process, you will have a built-in safety mechanism, which is venting. Cells, if they reach their high pressure because of gas evolution, they will actually vent. And they will vent to avoid explosions and other things. But when they vent, they have volatile material, and so you also need to make sure you have good ventilation. And at the end, when we see this happening, we need to be able to deactivate them or de-energize them and discharge them. And this way, avoid thermal runaway. So this is there is a lot of research together with first responders, second responders, the Department of Transportation, and many, many other entities that we're developing techniques and methodologies for if there are accidents. Why? Because accidents always happen in engineering and in any engineered system. Then we need to make sure we suppress the fire really quickly, we cool the pack, we can de-energize the cells, and we can tow away, isolate if needed, and then, of course, investigate the fire. So part of the BMS, like the black box, is actually keeping track of these signals and these indicators. Managing discarded batteries is extremely important. We have a lot of batteries. These are all these probably battery packs that you're using in your drills, right, and power tools. A lot of them have lithium-ion batteries, and we need to recycle them and put them in the right bin and be able to be stay away from the main waste stream for better management. And I'm saying this because it has happened that a lot of us, we don't even realize that something we're discarding in the garbage actually has batteries, lithium-ion batteries, and then you throw it and you can cause problems in the waste management facilities. incidents that have happened in the last few years have grown quite a bit when it comes to causes from lithium-ion fires in waste collection facilities in the waste stream, and of course propane cylinders as always. I want to close by saying that, mention to you that it's very clear that at the Automotive Lab, as I started, we have a responsibility to also not do research, but of course do a lot of education. And we're working a lot. We are really the ground zero here at the Midwest of a lot of manufacturing that is happening in internal combustion engines, parts supplies, and assembly plants. And so we are working very hard in trying to really upskill and reskill and bring new students and many, whoever is interested and try to bring a lot of people into this new economy and the new plants with this new technology so that we don't see problems, economic growth problems in our region. The industry wants very much this type of skills, battery management, a highlight here, system design, battery testing, of course materials, but electrical skills. And industry says actually right now that 90% of industry identified limited number of applicants with required skills. 44% of the industry, the industrial leaders that they were interviewed, did not find local applicants with required skills. So we need to ramp up the education aspects, and the battery management is great because it has a lot of applications, not only in the automotive sector, but also the grid. So it's a great place to be, and thank you very much for your attention. So Roy will moderate the questions.
Thank you so much for that great talk. It's really interesting to take a peek behind the curtain of all of this work that's going on to improve batteries. It's highly technical, as you can see, and that, of course, raised quite a few questions. We'll try to get through them in the next half hour. And let's start with one interesting question to do with the scaling of batteries to the required range of, say, an electric vehicle. A lot of people would like the range to match that that comes from gasoline or diesel, which may be, 500 miles per tank. So how does that scale with the size? Considering that the area, the footprint of a car is sort of more or less fixed. So that means making the battery thicker and heavier.
Yes.
So could you say something about scaling? Is it a linear
actually, thank you. So I actually had a graph. It's an eye. Again, it's a lot of information in there. But it is a good question, and it is a valid question. What is the appropriate size of a battery? Ideally, if most of us are not really traveling. Well, let me show you the graph first, and then I'll make some arguments. So the data, and this is a report that was just issued from Arbor National Laboratory across all, actually, collaboration across national labs and industry. And what you see here is a battery electric vehicle with 200 miles, 300 miles, and 400 miles greenhouse gas emissions. Of course, the bigger is the pack, the less, well, there is a lot of energy in it captured. and needed to manufacture this. And of course, it's also heavier, like you said, and bigger, and therefore there's also less fuel efficiency. But still, it is, when it comes to environmental impact, it's still, as you can see, even the current practice, the greenhouse gas emissions per mile is much lower than the current practice, and these are the best current practice available, or at least models that are out there from many other applications. This is plug-in hybrids that they're near, you can see, closing by, inching by. So plug-in hybrids that have a small 50 miles battery are actually very close to a BEV currently of 400 miles. So now the issue is that we don't drive 400 miles. You will probably drive maybe once or twice a year, most people. And we typically drive something like 20 miles. And okay, maybe 50 per day. And you will have the opportunity to charge overnight. And therefore, it is actually, I don't know, I want to say liberating. I don't even have to go to a gas station every week to fill up my tank, because most of us, we should be able to charge on our home with the level 2 charger. 75% of the United States have driveways or garages, but I don't actually. And that's why I cannot have right now a battery electric vehicle, but I'm using a scooter. So yeah, the smallest the better, and in fact, both economically and environmentally, and it makes sense to produce battery electric vehicles that they have 40 or 50 miles range, and definitely not 400.
Thank you. This is another interesting question that a lot of people are obviously interested in it, and it's to do with battery cell cost. And this question would like to know, what are the key enablers to lowering cost of battery production other than scaling? Obviously, scaling is a very important aspect, but other than scaling, what are the other key enablers?
It's materials. Materials are expensive. Their processing is very expensive. And at the end, so energy density is so important, and there is a lot of research going on in improving energy density, because that means that at the same time you're making it lighter, but it has less material. That means actually more affordable. So materials, energy density is extremely important. As we are moving towards batteries that they have in their anode silicon, that can actually store a lot more lithium, and it's about the same weight with the graphite. We are actually going to improve, and it's less expensive. We will reduce the cost as we move to lithium, solid-state lithium batteries that are happening also near the automotive laboratory and many other places. We will improve a lot of the cost. It's also important to know that sourcing this material, of course, it's very important for the cost. We have seen the nickel price going up dramatically the last 2 years, last year with the war in Ukraine, because a lot of the lithium is produced, nickel is actually sourced in Russia and various areas that have been impaired by the supply chain disruptions. So being able to build up our domestic supply chain is extremely important for the cost.
Thank you. There's another interesting question here, and that is to do with the construction of batteries and the geometry. Is there an ideal geometry? There's a geometry in which the elements are stacked as a series of plates, or there's another one where the elements are in a row. And are there thermal management issues related to both of those geometries and other geometries?
Right, so that's a great question also. Maybe I can show you a picture so you know, I think it's important to realize there are many issues, right? We know what we need to achieve, the power and the energy density, because the energy density is the range and power is the acceleration that you need to have. And then we basically have to put many cells in parallel and series, sometimes, you know, many, thousands of them. This is a picture that for small cylindrical cells, you need something close to 7,000 of them. It is a very complex issue, the size. Are the prismatic, right now we have prismatic pouch and cylindrical cells. And by prismatic, I mean this kind of can, like an encased little can. So there is a cooling issue. The cooling, the best cooling actually is a combination of tab cooling and surface cooling. So tabs, where the current comes in and out, get pretty hot. And that's where a lot of the thermal conductivity, the aluminum and the copper are actually where we can take the heat out. Because the active electrode material are actually not thermal conductive. They have much worse thermal conductivity. So cooling the tabs and creating a cooling structure that will maintain the temperature is very important. And from then on, safety issues are also very important. Cylindrical cells are so used and were used in the past for quite a while because they have embedded in them circuits that will actually shut down the cell if the temperature increases at the level. So they have mechanisms, built-in mechanisms that they will do that. They don't rely on, you know, our software. The software is on top of that. Pouch cells are not so easy to embed this type of mechanisms, and therefore we're still evolving. We haven't concluded yet. The short answer is to be determined.
And a related question to the geometry question is what is the most convenient geometry for recycling, taking the components apart? Is there a preferred geometry that leads to an easier process of recycling?
Yes, that's an excellent question. So as I said, for safety, having a can, having a firm boundary that you can attach a lot of internal safety fuses and things like that, and positive coefficient thermal material that will stop the current is great. But then, the can is adding material weight, and also it's kind of hard to extract. You have to cut it, and laser cutting and other things need to be involved. So with pouches, it's probably much easier, and the pouches are thin and less material to discard if you need to discard them. So I don't exactly know. I think there is a lot of research on that on the Faraday Institute, actually in England. From places like Warwick, University of Warwick, and also, they have an energy institute there, they call it Faraday, and they do a lot of research on that topic.
There are obviously quite a few people in the audience who are looking at the numbers and the cost and considering switching over to EVs, and the cost of the vehicle is obviously a concern. So one question here is, the battery cost is 30 to 40% of the cost of an EV. Does that explain the cost difference that perhaps you go and buy a car now, a conventional gasoline internal combustion engine car, there's a cost differential? Is that mostly the battery, or is there some other considerations? I imagine the manufacturability of an electric vehicle, maybe not right now, but in the near future, will be a lot easier and a lot more cost efficient than an internal combustion car. So could you say a few words about that?
The fact now is that they are more expensive for all these reasons we discussed, like the materials, it's an infancy. The processing, the actual manufacturing of the batteries are, it's a highly automated, precise, dry environment that takes energy and know-how that right now we are developing, and so the cost will go down by improving and scaling up the manufacturing. But in principle, the battery electric vehicles are going to be actually potentially cheaper because they're simpler, sort of less. There are less different parts. The powertrain, what we call the powertrain, which is the batteries all the way to a very simple transmission, and then power goes to your wheels. Whereas in a internal combustion engine, there are a lot of other many parts that we have developed and improved and perfected. But the complexity is higher. So in principle, we should actually see lower cost, but we have to work really hard to do it.
Thank you. There's a related question in terms of the extending the lifetime of a car battery, since it's so much of a large part of the operation of an EV. Are there other simple ways to extend the battery life? The person who asked the question is making an analogy with the refrigerator, where it does a defrost cycle. Is there something that is possible in terms of a lithium oxide cycle, or?
Yeah, to do a rejuvenation, right? So I think we will be finding, going forward, actually ways of, slow down and extend life. Slow down aging and extend life. And we are getting better and better and better. In fact, most of our electric vehicles are lasting way longer than what we had anticipated. Now, part of the total cost of ownership is well known, is the fact that you don't have maintenance, oil change and things like that. But the truth is that we might end up having something that it's not a maintenance, but it's like a cycle that would, first of all, take the vehicle through a cycle that will, first of all, inform the BMS about the real state of the health of the battery, and perhaps do some adjustments. So I think we might see in the future a little bit of this, checkups periods where you would go and check your electric vehicle and all the system will, via the cloud, will recalibrate and have a new BMS. And the battery management system, in fact, it's so powerful. It can actually extend change the power denials in a sense, right? So you can feel rejuvenated occasionally with your car stretching the range through software.
So that kind of leads into a set of materials-related questions. Are there, in the future, perhaps, is there a possibility for the development of other materials, for example, to replace the graphite matrix of the anode with another? There are many sort of lead two-dimensional materials now that are being studied from a
graphene
solid state point of view. Could you say a few words about what the future might look like for materials?
Yes, that's that's a good question, and as you can see, I had some backup slides here because, as always, as I said, materials are very important for the cost. So we have started. Oops, hang on. Let me see. Okay. So as you can see, we had originally a lot of cobalt and a lot of nickel. We're moving towards a mode, like most of you that you're using lithium-ion batteries, we are now in this chemistry, which is nickel, manganese, cobalt, and the lithium. And as you can see, this trajectory shows more nickel. The high cost of nickel, of course, recently kind of like put some brakes on that trend. Basically, what we're trying to do here is remove cobalt. Cobalt is sourced in Congo, and so it's problematic, highly problematic, and it's controlled and traded in pretty obscure markets that we can't keep track of. In the future, so that's what happens in the cathode. There is a lot of things that happen also in the anode. As I said, the battery has like two sides that we are always looking for improvements. In the anode side, we are now on this stage where we have a lot of graphite separator, the cathode. We are looking into silicon-enhanced anodes where there is a small to a high % of silicon. And then eventually, and there is, this is a little bit like our holy grail right now, where we will have ultra-thin lithium metal, not graphite, right? Graphite in some sense is, it's just bulk, it's just a host. So if we can get rid of it and just have the lithium go back and forth, then that's ideally the case. The problem is that this lithium will need a new electrolyte, solid state electrolyte. This new electrolyte is extremely important because it will also improve at the same time the safety of the battery. It doesn't have volatile organic material that actually creates some of this gas evolution and some of the safety fire propensity. So yeah, it's all good. So this, I mean, there's a lot of work to be done for this to be achieved, but that's the plan.
That also brings up another question to do with materials, and that is, traditionally capacitors have been a way to store electrical energy. Now, with modern R&D, there's supercapacitors, which have a much higher storage capability than conventional capacitors. Is there a way to combine battery design incorporating capacitors, which have generally speaking, have a more more lifetime, more cycles to the lifetime, and perhaps even faster charging. Could you say a little bit about that kind of aspect of battery research?
Excellent question and suggestion. And in fact, there is a company, I believe, that here locally that is doing that in Michigan. It's I think it's called Our New Energy One, and this is a graph here that shows for all of us. Here I put sorry. So this is this brings capacitors, ultra capacitors, lithium-ion batteries in the energy power axis. And so indeed, as you can see, and so what you see in these lines are dynamic response, let's say, time, right? So what you see here is like lithium-ion batteries, of course, are better than lead acid and nickel cadmium. I mean, that's why we moved here. But when it comes to fast response and actually cycling time, ultracapacitors are obviously much better. They are expensive, and merging them correctly will also require power converters that will actually settle the energy and balance the assets between the battery and the capacitor. And so that adds to the weight, to the cost, to the complexity. So there is, it's a tricky thing to achieve. If you can do it only with one battery, that's great. If we need to consider capacitors, I believe there are companies that are working on it. In applications like regional flying, probably you've heard the electric flight is extremely important. Nowadays, a lot of small startups are working on creating small planes for regional flying to also help rural communities and remote areas. So for these, there is a need to have capacitors because of this high power you need to land and to take off. For power, high power demand systems like perhaps semi-trucks, mostly cruise. So it depends. It's a very application-specific answer, but there is a place for that. And I think some of you are paying attention, if I may, on where fuel cells combustion and is in this graph. This is, bear in mind, it's a logarithmic scale. So energy-wise, of course, liquid fuels are carrying a lot of energy. It's really hard to beat, really hard to compete. And I just have to mention that for one travel mile, you also need quite a lot of chocolate.
Yeah, that's such a relevant point, because battery technology is such an important part of all of our devices that we use and all of our applications. So there's bound to be a use for lots of new ideas and that fit with a particular application. There's a set of questions that came in which are all to do with the carbon footprint of the technology, and they're really important questions. Obviously one of the main drivers of EV development and implementation is to reduce the carbon load on the atmosphere. And on the other side of that coin is that the manufacturing and production of large quantities of battery materials also has its, you touched on this in one of your slides, also has its carbon footprint. So the question is, how do those things fit together in the bigger picture of battery technology?
Totally, that's right. This is the, as I said, I'll go again to this graph. This graph this report is excellent. It has so much information. So in this graph, what you see at the bottom, this blue or cyan, lines correspond to the production burden. So batteries create emissions, sort of upstream emissions, right? Like there's no tailpipe, but they create emissions because they are produced, mined, and processed. And of course, they make emissions because it depends on where the grid, if the grid that they were charged from was a grid that had renewables or not, or has coal production, electricity or not. So these numbers here correspond to the blue, the cyan numbers correspond to the production burden. So that is mining, processing, manufacturing. As you can see, batteries are above the gray line, so they are bigger than an internal combustion engine. Okay? It's true. So a battery makes emission at its birth before it gets out on the street. But it will quickly, as this graph shows, that correspond to the total greenhouse gases per mile, that includes the cradle to grave, includes these blue lines, will immediately, so these black lines correspond to the total greenhouse gas emissions. That includes production and grid, average US grid emissions. So it's not just, it's equivalent, so this grams CO2e per mile, it embeds all of this emissions, and that's why a battery electric vehicle, that it's different size of battery, has different values up here. You see? Okay. So again, you're right. As we decarbonize the grid, in fact, these lines will go down. So the grid is extremely important. It's not only charging the batteries, and therefore its greenhouse gas content is very important for the battery electric vehicle. The grid also powers the manufacturing that the batteries are made from. So if we manage to do manufacturing in the US where we have cleaner grid, will be also better for the greenhouse gas emissions content throughout its whole life of a battery. So cost will go down, emissions will go down, people will have amazing employment, and so I think hopefully.
Thank you. It's very interesting that as we speak, there's a major conference, COP27, going on in Sharm el-Sheikh, Egypt, at which these issues are being actively discussed by leaders across the planet. And one of the big elephants in the room is, will we have enough generating capacity of electricity to handle the predicted growth of EV technology? And will that generating be done with environmentally friendly processes? Overall, will it reduce the carbon footprint? So one question is that, if all these 2,000 prismatic cells per minute are being produced, how much more electrical generating capacity? This is really a rhetorical question, so you don't have to. But how much extra power and power plants will we need to have, and of what kind? So this is maybe a little bit beyond where your research goes, but
it's totally beyond my research, definitely. But I've been these are the very important questions, right? The cost, life, safety, and then basically the environmental sustainability aspect of the battery. So, okay. So the first question, it's the grid. Will the grid handle this extra charging, let's say, right? Just the vehicle charging. Let's say I bought it, it was manufactured somewhere else, and I bought it, and I have it now. Let's say everybody buys vehicles and charges it. There are some places in the United States that actually will need transmission grid improvements, like considerable grid improvements. And of course, it's important to create and install a lot of renewables and use actually batteries to store energy to improve the reliability of the grid or maintain the reliability of the grid. There are areas, like I said, that it will need grid improvements, but in the general case where we have chargers that they are networked, this should not be a big problem. That means networked, so a vehicle charging would be a controllable load. So in fact, it will help the renewable penetration to the grid. Why? Because you can just stop charging, if not do the other way around and help when there is a high peak and there is a high demand. You can actually, and high cost in the grid, we now have vehicle-to-grid integration in some places in California where you can actually use your vehicle to power your building, your own home, and therefore reduce, or you can just create a nano grid, a small grid with your solar power wall or small storage and your vehicle to actually be less vulnerable to price variability from the electricity side. So in fact, it's actually good. The projection is very good. When it comes to adding manufacturing, all the entities that they're adding manufacturing, battery manufacturing in the United States, them being either US companies or non-US companies that they are installing new battery manufacturing facilities in the US, they're installing also a lot of solar on the roofs and around it because they know that these facilities need a lot of electricity because of the dry rooms. Batteries are made in dry rooms, and there is fascinating how they're made. It's like bread making. And
we're getting toward the end of our time, but I want to finish up with one last question, which is to do with what power levels can this technology go to in terms of transport, both on the ground and also in the air. Heavy vehicles, tractor, trailer, transportation, large airplanes. Is that all in the future? Is it realistic to think about those things?
Yes, of course. Thank you. Yes, thanks for this question. It's pretty clear that there are large transportation systems and long-range aviation and marine that will require hydrogen and fuel cells or synthetic fuels that are made out of hydrogen and CO2. So ideally, we should create, there is a lot of work. And again, it's not batteries or fuel cells, it's and. We are in an era we have to do both. We have to do everything that is possible that starts from a low carbon intensity fuel. That's the important part. So internal combustion engines are great as long as they are better. They would be amazing if we managed to create synthetic fuels that are made out of hydrogen and CO2.
Okay, well, thank you very much, Anna, for a wonderfully insightful talk. The hour has been reached, so we'll wrap this up by thanking all of our sponsors for their generous support of Saturday Morning Physics, and to you, the audience, for being so loyal and for asking so many very interesting and probing questions into what is essentially a new technology being developed from basic science. I want to also wish you and everyone a happy Thanksgiving holiday. Don't forget to pick up one of your a cookie on your way out in the form of a block M. And we look forward to seeing you again after Thanksgiving. And thank you so much, Anna. That was great.